Okay. So we continue on the next topic on the method of analysis. Okay. So as I told previously, okay, because we have the resisting force and also the driving force. Okay. So we call it is a limit equilibrium methods. Okay. So the factor safety is the shear strength at the time of failure, okay, because it's tau F, compared to the stress acting plane, which is tau M. Okay. So if factor safety is 1, okay, then the slope is in critical conditions. Okay. So at the time of failure, the shear strength, okay, of the soil is fully mobilized along the failure plane. Okay. So the shear strength is represented by the Moore column criteria. Okay. In the slope analysis, in the slope stability analysis, okay, we may use two types of analysis based on the total stress approach, okay, or based on effective stress analysis. Okay. So for instance, for the total stress analysis, okay, we only use the value from the CU, okay, where we not consider the effect of the pore water pressure, okay, because the total stress is a sum of effective stress plus of pore water pressure. So it is embedded in the total stress analysis. Okay. While for the effective stress analysis, okay, the value or the equation that we use, okay, is the C, okay, plus the normal stress tangent phi. Okay. So that is the shear strength parameter or the tau F. Okay. In relation to the shear strength parameter to be used in the slope stability analysis, it is important to know the time when the most critical state occurs. Okay. If the most critical condition is predicted at the end of its construction period, a short-term analysis should be used where we use the total stress concept, okay, and it is more appropriate compared to the effective stress analysis, or we call as a long-term analysis. Okay. So on the other hand, if the critical condition is predicted in the long-term situation, then the effective stress concept is to be applied. Okay. So this depends on the type of the slope in question and on the type of soil. Okay. So normally, okay, in analyze the slope stability, okay, I prefer to use the long-term analysis, which is the effective stress analysis, rather than the short-term analysis. Okay. However, we can make both analysis, and normally we may use the most conservative value. Okay. For example, the most critical condition for excavated slope is the long term. Okay. While the most critical condition of the embankment slope is the short term. Okay. So short terms is referred to the end of the construction periods. Okay, means that right after we complete the construction, So we use the short-term analysis. Okay. For slope made of low permeability soil, such as clay, the undrained assumptions may be more appropriate since the dissipations of pore water pressure will take a long time. For high permeable soil, such as sands, where drainage takes place almost immediately, we use the effective stress parameter C and phi. In relation to the type of failure surface, the subsequent parts will deal with slope stability analysis for infinite slope, which is related to the transitional type of failure, the analysis of finite slope with planar surface of failure, and circular failure for undrained conditions. Evaluation of slope stability for a more complex situation should be analyzed using method of slices. Okay. So this is a part of explanations on the type of analysis based on the slope structure itself. Okay. So for example, for the infinite slope, okay, we may use the transitional type of failure. Okay. While if we do infinite slope, okay, so we may use the circular failure for undrained conditions. Okay. However, okay, normally when we carry out for the analysis of the slope, okay, so the common type of methods for the finite slope is the method of slices. Okay, so you may learn later on, okay, on the method of slices, okay, where we may use the Bishop's approach and also the Frillenius approach. Okay. Causes of slope failure. Okay. The first one is the slope inclinations. So additional load of field height, loss of shear strength due to weathering, liquefactions, water, vegetations, type of earth material. Okay. So we have 6 main causes of slope failure. Okay. So the first one is the slope inclinations. Okay, I have mentioned several times. Okay. To ensure the stability of the slope, so the slope degree should less than the friction, internal friction angle of the soil. Okay. So the type of the earth material also contributes to the slope failure. Okay, we may discuss later. Okay. And also the vegetations that grow, okay, on the slope surface or on the toe and also on the top. Okay. So the loss of shear strength, okay, so this is the intrinsic parameter, okay, where the strength of the soil contributes either either could increase the stability or could reduce the stability. Okay. If the strength has reduced, okay, so it can reduce the stability of the slope. Okay. And normally this situation happen due to the weathering, liquefactions, and infiltrations and seepage of water. Okay. So weathering is more related to the rock slope, okay, due to the hot and wet conditions and also due to the wind. Liquefaction is due to the earthquake event, okay, where the vibrations, okay, from the bottom or from the epicenter, okay, could make the soil, okay, become like a liquid. Okay. So the last one is the infiltration and seepage. Okay, most probably due to the rainfall and also to the to the groundwater level. Okay. So the climate change, the climate change also contribute to the cause of the slope failure. Okay, because nowadays, okay, we can feel that the temperature is getting hotter, okay, and at the same time the rainfall intensity is 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 increasing with time. So additional load of field height, okay, may contribute to the failure of the slope. Okay, so we need to make sure that any structure should be built far from the top slope. Okay, and also to reduce the effect of the field height. So in that case, that's why we need to have the berm, okay, to reduce the what we call as the effect of the field height. And also we need to make sure that, okay, the compaction effort, especially for the embankment, okay, should follow the maximum dry density from the compactions laboratory testing. Okay, it should 95% from the maximum dry density value. Okay, so this is the cause of the typical cause of slope failure. Okay, the last one is the excessive pore water pressure. Okay. So this is due to what we call as the increment of groundwater level. Okay, most probably due to the rainfall as well. Okay. So the role of the slope inclinations, okay, his slope angle is a measure of the steepness of a slope. We call it a slope gradient. Steeper slope increase driving force, as we have discussed previously. Steep slope associated with rockfall, okay, subarid to arid environments. Okay, so this is the locations may contribute to the environment. Slope form for the role of the earth material, slope formed by a weak rock such as shale or have thick soil deposit typically fail by rotational slide. Okay. Slope formed by the hard rock typically fail by a transitional slide. Soil slip occur above bedrock and fail by transitional slides. Okay. That means that we need to take care on the type of the shale formations. Okay. So if the shear formation exposed to a water, so it become a weak material. Okay, same go to the limestone. Okay, but the limestone is formation is normally occur on the flat area, but for the shale, okay, it can be found on a hilly area. Okay, especially what happened in Kedah previously. Okay, there are some formations from shale material of shale formations. When they're exposed to the water, so it become weak. Okay. Role of vegetations in subhumid to humid environment. Vegetation is thick and abundant. The landslide activity includes deep, compact landslide, earth flow, and soil creeps. Okay. So vegetation influence slope stability by providing a cover that cushion the impact of the rain falling on slope and retard erosion on surface. Okay, so that is the function of vegetations. Okay. So vegetation has root system that tend to provide an apparent cohesion which increase resistance to landsliding. However, vegetation add width to the slope increase the driving force. Okay. So in that case, okay, so the maintenance is the most uh, uh, appropriate method, okay, in order to balance, okay, the functions of the vegetations on the slope surface. So if we do not take care on the vegetations, it will provide a disadvantage, okay, due to the additional weights, okay, on the slope surface. Okay. So role of weathering, physical and chemical weathering can weaken slope material where decreasing the resisting force. Okay, so this is a typical example of the grade or of the weathering grade from the grade number 1 to the grade number 6. Okay, the grade number 1 is the fresh rock. Okay, and due to the rock has been exposed, okay, on the physical or chemical weathering, so it can decrease the grade number, okay, from 1 to 2 to 3, and the most worst condition, it will become to grade number 6, okay, which is a residual soil, like laterite soil. Okay. Water can affect the slope stability. Okay. Shallow soil slip can develop during rainstorm when slope becomes saturated. Okay. Slump or transitional slide can develop month or year after the slope is saturated. Okay. Water can erode the base of toe of a slope, decreasing slope stability. Okay. So actually the water, the amount of water should be controlled. Okay. Because the water can contribute to the uh, to the driving force, because the water has their own weight, okay, where the unit weight of water is 10, okay, so it can contribute to the driving force because it has its own weight. Okay, so normally for the slope structure, okay, the installation of a horizontal drain, okay, could minimize the effect from the water when it penetrated inside the slope structure. Okay. So role of climate. Climate influences the amount and the timing of water in the form of water or snow. It also influences the type and amount of vegetations. Okay. Triggering mechanism. Okay. Intense rainfall. Okay. Where it related to the increment of pore water pressure. Okay. Or excessive of pore water pressure. Erosions. Okay. Removal of toe support and increase the slope angle. Okay. So to solve it, so we need to, for example, to construct a gabion wall on the toe, and then to use a hydro seeding methods to plant for the vegetations. Okay. earthquake loading, okay, it can contribute to the driving force and make the soil become liquids or behave under a liquefaction. Okay. Construction activities, okay, so this is some example of construction activities that can contribute for the decreasing of the factor safety, okay, especially when the excavation has been carried out on the toe. Okay. Surcharge loading, okay, and rapid drawdown. Okay, so this normally happen at the reservoir area, okay, where it has a sudden increment of water level, uh, decrease of water level. Okay. Okay. Type of failure, we have three common type of failure. Okay. Wedge failure is the soil mass movement due to external force. This type of failure usually occur on a weak plane or weak joint. Okay, so when we see the the term of joint plane, so normally it related to the rock structure. Okay, rock slope structure. Okay, so the second one is secular failure or non-secular failure. Okay, so this is more related to the slope of soil. Okay, where for the secular failure are associated with homogeneous soil condition. Okay, where the soil is similar, okay, type. While for the non-secular slip are associated with non-homogeneous conditions, where the soil is not on the same, or it has a multi-layer of soil. Transitional failure occur when the form of the failure is influenced by the presence of weak layer. The failure surface tend to be plain and roughly parallel to the slope surface. Okay. So this example of the wedge failure, okay, so normally happen in the rock slope structure, okay, and we will not discuss in our detailed calculation later on. Okay. So this is secular failure or non-secular failure. Okay. So normally it is used to analyze for a finite slope. Okay. So this is a location in front of M47 in SKA, School of Civil Engineering. Okay. I guess most of you miss this block, okay, M47. Okay. It is almost 2 years. No students, okay, or there are no face-to-face lecture, okay, in this block. Okay. So this is a slope we consider as slope failure. Okay. So this is not a good practice, where they cover with half of this blanket. Okay. So we just want to share with you to show this is not a good practice. Okay. So it's a part of our learning process. Okay. So if you work with the authority later on, so you need to cover full. Okay. Okay. So this is the type of the secular failure. Okay. So if it has a multi-layer or more than one layer, so we can have a non-secular failure. Okay. However, the approach is still same. Okay. Either we want to use the total stress approach or the method or the stress based on the method of slices. Okay. So the last one is the transitional failure. Okay. Where normally we use to analyze for an infinite slope. Okay. So infinite is stand for infinity. Okay. But it doesn't have any toe and top. So we assume it is has a very long length of the slope surface. Okay. So this example, okay, to show that there are a movement happen, okay, on this particular area because it doesn't have any geometry. It's very not easy to identify. Okay. Okay. So there is another type of failure, okay, uh, which is I share in this diagram. Okay. So transitional slide, okay, weak layer. Okay, they have a weak layer there. Okay. Rotational slide, there is a common. Actually, this is a same with the previous three. Okay. Rotational slide, okay, where it happened on the toe slide, on the toe. Okay. Rotational slide for the slope number 4, okay, where is this slope slide, okay, and flow slide, okay, this is debris flow, viscous fluid behavior, and this is a block slide, okay, when this part will be moved as a block, okay, due to it has two different water reservoir. Okay. Okay. So in terms of the failure modes, okay, we can compare in terms of the velocity of mass movement. Okay. For the lateral spread is slow. Okay. And then it increase when the failure is rotational slide and increase when it behaves as a debris flow. So the last one is the rock fall, okay, because the mass of the rock or the volume of the rock is very high. Okay. For example, in 2003, okay, if you still remember, okay, where an incident happened at NKVE, North Kelang Valley Express, okay, where there are a huge of rock structure, okay, fall on that NKVE lane. Okay. So there's although there are no fatalities, okay, no one has been killed, okay, or injured. However, they need to close the road for more than a month, okay, and the cost to remove all this structure or this rock mass, okay, almost reach up to 1 billion, around 800 million. Okay, it's very huge amount of money. Include the treatment, okay, on that area. Okay. Okay, this is example of toppling instability, okay, where it more related to a rock structure, rock slope structure. Okay. So this example of the flow, debris flow failure. Okay. So this another example on rotational slide. Okay. So they experience the whole structure that fail, okay, due to this rotational slide event. Okay, so this example of the block slide, as we have discussed previously. Okay, so however, some of the example we may not discuss in detail, okay, in terms of to obtain the factor safety value. Okay, so but I want to explain several type of failure. Okay. Okay, important type of mass wasting. Okay, so mass wasting is the wasting or the what we call as the movement of the soil. Okay, so they use the term of mass wasting. Okay, so this is the slide type. Okay, downward movement of the coherent block of earth material. Okay, so they have a slump sliding along a curved slide plane, producing slump block. Okay. So they have a fall there, rock fall from the vertical face, flow, down slope, movement of unconsolidated material, and in which particle move about and mix within the mass. Okay. Subsidence, sinking of a mass of earth material below the level of surrounding material. Okay. So this is type of soil movement or mass wasting. Okay, so this example in a diagram, okay, where a slump type or slump block or the block, or the circular block type of failure. Okay, so this the scarp is the top. Okay, humoki is the type of a type of sandstone material or sandstone soil. Okay. So this example of slump, okay, or a rotational failure. Okay. Whether it's the top or the scarp. Okay. Okay, so we can see that there are different there. Okay. Between the existing where and the failure. Okay, while for the debris flow are the downslope flow of relatively coarse material. Okay, 50% of particles in the debris flow are coarser than sand. Okay, so means that it's very heavy. Okay, in some part they can bring along a big boulder. Okay, for example, in the Jelapang, the size of the boulder, in Nian Kedah, the previous debris flow event, the size of the boulder is approximately reach 1 meter diameter. Okay, movement may be very slow or very fast depending on the topographic conditions. Okay, mud flow, debris avalanche, and debris flow. Okay, so it's very risk. Okay, especially for is that if there are any residence area like village, small village, okay, or people that live nearby that area. Okay, so it's very high risk for them. Okay, and it's very difficult to predict. Okay, because it may occur within 100 years. Okay, okay, because with the in Malaysia we do not have a very proper inventory, okay, to record previously 30 or 40 years ago. Okay, so we doesn't have any proper landslide inventory. Okay, but now we have a proper way to record for any events. Small to moderate magnitude event, occasionally large magnitude events. Okay. So this example of the drainage flow. Okay. Okay. So rock slide, rock move because there's nothing holding it back. Generally require a pre-existing low friction surface. Okay. So for example, this sandstone, okay, can move easily because they are being underlain by the clay beds. Okay. So like a clay layer, once it is wet, so it can become weaker, okay, and then may make the sandstone to move. Okay. So earthquake, okay. So this has been recorded in 1959. I guess this image has been recorded after that, okay, where 28 deaths, okay, in the earthquake leak. I'm not sure where it's empty, what is empty, or name or locations. Okay, so this is event due to the earthquake. Okay, so conception of equilibrium is slopes in equilibrium with their environment typically exhibit. So this is the normal condition, concave, straight, and convex. This hill slope profile shown at the left. Okay, so this is in equilibrium situation where they are not exposed to any erosions. Okay, slope out of equilibrium typically exhibit anomalous, okay, hummocky profile shown at the right. Okay, so there is different after it's been exposed to several years on due to the climate. Okay, so stepped topography. Okay, so this is the shale. Okay, where the shale is very need to have a need to put a proper attention. Okay, stepped topography is not necessarily indicative of instability, but it can be structurally controlled by underlying stratigraphy as shown here. Shale are most often associated with landslide. So they highlight as a red in color. Okay. In some occasion, there are no problems with this kind of stepped topography, but we need to identify what type of material, what type of formations. Okay, for example, if consists of shale, so we need to pay more attention. Okay. So out of equilibrium slope, okay, for example, slope that are experienced rampant erosions are typically out of equilibrium and exhibit truncated concave slope profile shown at left. Okay, so for this case, it's exposed to what we call as to wind and wave. Okay, so can have a high potential to be eroded. Okay. So the slope profile is also influenced by runoff requirement and the relative position of controlling base level, okay, as sketched here. Okay, not change in hill profile as channel move away from the ridge line. Okay, so this example, okay, especially due to the slope exposed to water, to rainfall, to river. Okay. Okay. So it changed, okay, from the step number 1, okay, and 2, and sudden it show to the condition at number 3. Okay. So continuation of an erosive cycle with gradual shift of the hill slope profile, resulting in homokey topography. Homokeys are typical of slope experience land slippage. Okay. Okay, so this is start of failure occur on this hill slope. So example of homokey topography. Okay, homokey topography is usually indicative of solid fluctuations or active land slippage. Okay, because this is more related to a geological engineering. Okay, so I'm not very familiar on this homokey type of material. Okay, so actually it's a sandstone type of material. Okay. Okay. So with that, I have provide a lecture on the introduction of slope engineering, slope stability analysis. Okay. So by the next week, okay, we may discuss, okay, on the limit equilibrium, okay, approach, okay, on how on how to derive, okay, the equations, okay, for the factor safety based on the limit equilibrium. Okay. So I guess for today, okay, enough for today. Okay. So we will meet next week, okay, on 2 o'clock. Okay. Then I will share the recorded version in the e-learning. Okay, but please give me a time, okay, because I want to upload it. Okay, but before that I need to wait for the webback to email me the full recorded version. Okay, give me 2 or 3 days before I upload in the e-learning. Okay. Okay, so with that I end my class. Okay, we meet next week. Okay, so Assalamualaikum and good afternoon.
Do we have attendance for today?
Oh, actually